This is Dreamtime Science, where we paint the canvas of your dreams with the soft brushstrokes of scientific wonder. Together we'll explore the mysteries that dance at the edge of consciousness. You know what's fascinating? I've been thinking about how every single thing around us, from the softest pillow to the stars we see at night, is made up of just a handful of building blocks called elements. Tonight I want to share the story of the periodic table, a kind of alphabet for the universe that's full of surprising connections and little secrets about the world we live in. It's like learning the ABCs of everything, and I think you're going to find some of these letters more magical than you ever imagined. Should you find solace in these cosmic lullabies, consider becoming a regular dreamer by subscribing. Share what topics intrigue your curious mind in the comments below. Now, take a moment. Adjust your blanket. Find the perfect hollow in your pillow. Let your shoulders melt. Breathe in and out. Long before the world was neatly mapped into continents and nations, before the lines of latitude and longitude crisscrossed the blue of ocean and the green of valley, humanity looked out over the land with hungry eyes and named what it saw: stone, water, flame, air. The impulse to classify, to seek order in the riot of existence, is as ancient as myth itself. As dusk drapes the hills and the hush of night draws near, let us travel back, not just through the centuries, but through the deep corridors of memory and imagination, to a time when the very notion of an element was both a mystical vision and a practical puzzle. The idea of elements as the fundamental stuff from which all else is made is a story told in many tongues and scripts. To the early Greeks, the world was a tapestry woven from 4 elemental threads: earth, air, fire, and water. Empedocles, with the gravity of a sage and the flair of a poet, spoke of these with reverence, imagining them as the purest essences, the bones and breath of reality. For ancient Chinese philosophers, another schema took hold: the 5 phases, or Wu Qing: wood, fire, earth, metal, and water, a symbolic dance of transformation, where each phase begot the next, cycling through creation and destruction, much as the seasons circle their familiar wheel. These early systems were not scientific in the modern sense, but they were not random either. They reflected the patterns people saw in the world around them: the solidity of rocks, the fluidity of rivers, the shifting, invisible currents of the wind. They were maps for living as much as for knowing. In these times, to name an element was to invoke power. Alchemists, cloaked in secrecy and paradox, chased the secrets hidden in metals and flames. Their laboratories, filled with the scent of sulfur and the glow of embers, were spaces of transformation, not only of matter, but of the self. They spoke of mercury, of sulfur, of salt, as primal substances that could be coaxed, persuaded, or tricked into revealing deeper truths. Their practices mingled prayer with experiment, and their journals, written in cryptic scripts, read as much like spells as they did like protocols. The myth of transmutation, the hope that lead could be turned to gold, was more than a material pursuit. It was a metaphor for the possibility that the ordinary might give rise to the extraordinary. As centuries passed, the dream of elements slowly shifted from the poetic to the empirical. The birth of modern chemistry was not a sudden revolution, but a slow unfolding, like the petals of a cautious flower. Each new discovery was a thread added to the intricate tapestry: antimony in the ancient Near East, phosphorus glowing eerily in the German night, platinum found in the sands of the New World. The names of the elements themselves are echoes of lost empires and adventurous spirits: tin from the old Cornish Stenum, copper from the island of Cyprus, tantalum named after a tormented figure from Greek myth. When the French chemist Antoine Lavoisier, in the late 18th century, began to catalogue the known substances that could not be broken down further, He did so with the cool precision of a taxonomist, but in his lists one can still feel the echo of wonder. He wrote of oxygen, nitrogen, hydrogen, sulfur, and a handful of metals, each a puzzle piece in a grand cosmic mosaic. The elements, once the property of gods and spirits, were now being gathered into the light of reason, but they retained their mystique. And yet these early lists were incomplete and sometimes confused. The line between element and compound blurred at the edges. The language of chemistry was still being invented, and every laboratory was a frontier. It is from this fertile ground, both rational and imaginative, that the idea of the periodic table would eventually spring. But before it was a chart hung on a classroom wall, before it was a tool for prediction and discovery, the periodic table was a dream, a vision of order amidst chaos. The 19th century was an age of cataloguing, of seeking systems. Naturalists gathered shells and butterflies, linguists mapped the branching trees of language, and chemists, increasingly, sought the deep order lying beneath the bewildering variety of substances. Each new element discovered was both a triumph and a challenge, an answer that raised further questions. Was there a pattern? Could all these disparate discoveries be woven into a single, coherent tapestry? The visionaries who first glimpsed the possibility of such order were both scientists and poets at heart. Johann Dobereiner, a German chemist, noticed that certain groups of elements seemed to share properties. Lithium, sodium, and potassium, for example, were all soft reactive metals. He grouped them into triads, an early hint that there might be a hidden symmetry at work. Later, John Newlands proposed that if the elements were arranged by their atomic weights, every eighth one shared similar properties, a law of octaves, as though the universe itself were written in the language of music. But it was Dmitri Mendeleev, the Russian chemist with the wild beard and restless mind, who gave the dream its most enduring form. In 1869, he arranged the known elements into a table according to their atomic weights, aligning them so that those with similar properties fell into columns. Where gaps appeared, he predicted the existence of yet undiscovered elements, confident that the order he perceived was not an illusion but a reflection of nature's own logic. When, in the decades that followed, new elements were discovered that filled these very gaps, it was as though a magician had pulled coins from behind the ear of the cosmos. The periodic table soon became more than a scientific tool. It was a symbol, a map of the invisible architecture of matter. It adorned the walls of laboratories and lecture halls, a kind of Rosetta Stone for the modern age. The order it revealed was both humbling and exhilarating. Here, at last, was evidence that the universe was not a random jumble, but an ordered whole, a symphony whose notes could be named and arranged. But the periodic table is more than a scientific artifact. It has become, in the years since its creation, a cultural touchstone, a source of metaphor, of inspiration, of playful homage. In literature, in film, in art, the table appears as a symbol of knowledge and mystery, of the quest to understand the building blocks of reality itself. In the gentle hush of a library, you might find Primo Levi's memoir, The Periodic Table, in which each chapter is named for an element, and the properties of zinc or iron become metaphors for memory, resilience, and loss. Levi, himself a chemist as well as a writer, weaves together the science of matter with the matter of human life, showing that the search for knowledge is always, in some sense, a search for meaning. In the world of visual art, the table's grid-like elegance has been taken up by painters and sculptors, its form echoed in installations and collages. Its regularity, a lattice of squares, each a window into the heart of an atom, suggests both containment and possibility. It is at once a fence and a gateway, inviting us to peer through and imagine what lies beyond. Popular culture, too, has embraced the table's iconic status. In comic strips and animated series, it is sometimes played for humor, a chart so intricate and mysterious that only the most brilliant or eccentric scientists can decipher it. In television dramas, the table often hangs on the chalkboard, a silent witness to experiments and epiphanies. In movies, it sometimes flashes by in a montage of scientific discovery, a shorthand for the idea that the secrets of the universe are, perhaps, within our grasp. Even fashion and design have borrowed its patterns. You might see the elements' symbols printed on t-shirts and coffee mugs, or rendered in jewelry, as though to wear a piece of the universe close to one's heart. There is something curiously satisfying about the cryptic elegance of Fe for iron or Au for gold, a code that is both ancient and modern. Beyond the classroom and the laboratory, the periodic table has also become a kind of template for organizing all sorts of things. There are periodic tables of fruit, of vegetables, of musical instruments, and even of fictional characters. This playful borrowing speaks to the deep appeal of the table's logic, the promise that with the right arrangement, even the most bewildering variety can be brought into harmony. But the table's cultural resonance goes even deeper, tapping into the old mythic longing to name the world. In ancient mythologies, to know the true name of a thing was to wield power over it. Wizards and sages, from Babylon to Camelot, were said to command the elements by uttering their secret names. The periodic table, in its modern guise, is both a continuation and a transformation of this tradition. Each element is given a symbol, a name, a place, its essence recognized and respected. The names themselves are a tapestry of history and imagination. Some, like helium, named for the sun, or selenium for the moon, recall the celestial bodies that have always inspired awe. Others, like promethium, honor the mythic figure who stole fire from the gods, a nod to the perennial human desire to harness the forces of nature. Still others bear the names of places, californium, berkelium, dubnium, or of people, einsteinium, curium, mendelevium, a subtle acknowledgement that our quest to understand the elements is always rooted in particular times and lives. There are stories, too, of rivalry and ambition woven into the table's history. Nations have vied to discover new elements, to win the honor of naming them. Laboratories have raced to synthesize ever heavier atoms, pushing the limits of what the nucleus can bear. Each new addition to the table is both a scientific achievement and a chapter in a larger human drama, a reminder that the pursuit of knowledge is never purely abstract. The periodic table, then, is not a static artifact, but a living document. It grows as our knowledge grows. It adapts as our understanding deepens. New elements, fleeting and unstable, have been coaxed into existence in the high-energy collisions of modern accelerators, their names added to the far reaches of the table like new stars on the edge of a map. The table's shape has shifted too, as chemists have debated how best to represent its underlying symmetries. Some versions are spirals, others are circles, each a different way of capturing the relationships among the elements. In all of these guises, the table remains a symbol of both humility and hope. It reminds us that the world is more complex than our first theories, more various than our earliest myths. Yet it also testifies to our capacity for pattern-seeking, for finding order amidst chaos, for weaving the facts of chemistry into the fabric of culture. So, as you close your eyes, and the boundaries of day and night begin to blur, let your mind drift over the quiet expanse of the table, each box a window, each symbol a story. Feel the weight of history in the names, the shimmer of myth in the symbols, the pulse of discovery in the empty spaces yet to be filled. Let the song of the elements linger in the silence, promising that beneath the ever-changing surface of the world there runs a deep and hidden order waiting to be revealed. In the next quiet hour, we will look closer at the table's design, not just as a cultural icon, but as a map with a logic all its own, a key to the hidden patterns that shape the very matter of our world. But for now, let the wonder of names and symbols drift with you, gentle as the hush of night. Beneath the gentle hush of night, let us wander deeper into the heart of matter, to the orchestra pit where the Symphony of Elements tunes its instruments. The periodic table stands before us, not merely a chart, but a cryptic score, each square a note, each row and column a phrase in the grand melody of existence. No mere catalogue of substances, it is a map of possibility, charted by curiosity, revised by discovery, and bounded only by the edge of the knowable. Within its stately grid, patterns ripple like the tides, periodicity, the echoing recurrence of chemical properties, the subtle dance of electrons in their invisible shells. What appears to us as order is a tapestry woven from the smallest quanta and the grandest aspirations of the mind. Let us peer closer, tracing the lines and spaces, listening for the harmonies and discords that hint at secrets yet unsolved. Begin at the upper left, where hydrogen perches alone, the lightest and most ancient of elements. It is simplicity distilled, one proton, one electron, a particle so basic and so abundant that it makes up most of the universe's visible matter. Next to it, helium, a noble gas, born in the cores of stars, stable and aloof. Already, the first row, the first period, sings of contrast, the reactive, the inert, the seeker and the sage. Yet as we descend, row by row, the elements grow heavier, more complex. Electrons fill their shells in a prescribed order, dictated by quantum rules. These rules, so abstract and mathematical, unfurl as a rippling pattern across the table. Each new period brings a new shell, a new layer of possibility, and the elements begin to display their varied personalities. Lithium, sodium, potassium, soft metals, eager to part with their outermost electron, quick to flare and fizz at the touch of water. Across from them, fluorine, chlorine, bromine, halogens, sharp and hungry, seeking to complete their electron shells, to snatch and bind with voracious intent. The table's architecture is no accident. The columns, called groups, gather together elements who share family traits. The noble gases, far to the right, form a line of recluses, their shells full, their chemical desires sated. The alkali metals, far to the left, are quick-blooded and impulsive. Between them stretch the main group elements, their properties shifting, blending, morphing as we move from left to right. Boron and aluminum, carbon and silicon, nitrogen and phosphorus. Each pair sings a duet across the table, echoing reactivity, bonding preference, even the architecture of minerals and the scaffolding of life. Yet as our eyes drift downward, the table bends in on itself, accommodating the transition metals, those elements that seem to defy easy classification: iron, copper, gold, platinum. Their stories are told in the colors of ancient coins, the forging of swords, the glint of jewelry, the hum of electrical circuits. Their d-electrons, neither fully shielded nor fully free, bestow upon them a versatility, a richness of chemistry that underlies much of the technology and biology we know. The transition metals are the chameleons of the table, their oxidation states shifting, their complexes dazzling with color and magnetism. Below these, the table splits, expanding to make room for the lanthanides and actinides, two wandering rows, often relegated to a footnote at the bottom. These are the rare earths, the actinides, elements whose names evoke myth and science fiction: neodymium, plutonium, americium, curium. Here the periodicity grows more subtle, the rules more arcane. Their electrons slip into F orbitals, spaces with peculiar shapes and energies, giving rise to properties that boggle the mind. The rare earths light our screens, strengthen our magnets, fuel our reactors and dreams of distant stars. The actinides, some born in the violence of supernovae, others forged in the laboratories of humankind, glow with radioactivity, a reminder that the boundaries of the table shimmer and shift, ever at the edge of stability. Consider for a moment the beauty of periodicity. The table's patterns arise not from arbitrary classification, but from the very nature of quantum reality. The structure of the atom, its dense nucleus orbited by electrons in quantized shells, creates a repeating motif. Each period, a new shell. Each group, a similar electron configuration. The properties we observe, melting point, reactivity, color, are all expressions of these deeper symmetries. The table is not simply a list. It is a manifestation of the universe's underlying order. But this order is not perfect, nor is it complete. As we gaze at the table, we find anomalies, exceptions that whisper of hidden depths. Hydrogen, for example, sits atop the alkali metals, yet it behaves in ways both metallic and non-metallic, sometimes echoing the halogens to its right. Helium, though grouped with the noble gases, fills its shell with 2 electrons, not 8. The transition metals refuse to fit neatly into patterns of reactivity or valence, and the lanthanides and actinides with their F-electron confusion blur the boundaries even further. What are we to make of these irregularities? They are not errors, but signatures, traces of the deeper rules that govern atomic structure. Quantum mechanics, with its strange prohibitions and compulsions, shapes the table's contours. The Pauli exclusion principle, the Aufbau principle, Hund's rule, all are woven into the table's architecture, steering electrons into their orbits, determining how elements will behave, combine, and transform. The table is a compromise between the ideal and the real, a map that reflects both the symmetry of mathematics and the idiosyncrasy of nature. Expand your gaze beyond the table's familiar borders, and you find the territory of the unknown. For centuries, the table was populated only with those elements that could be wrenched from earth, air, and fire: hydrogen, oxygen, sulfur, lead, gold. Yet as chemistry advanced, new elements were teased from ores, isolated by careful experiment: phosphorus burning with a ghostly light, platinum gleaming in the hands of alchemists, noble gases coaxed from the air. The table grew, row by row, column by column, each new element a prize plucked from the riddles of matter. But science, ever restless, did not stop at what nature offered. The 20th century brought with it a new alchemy, the ability to forge elements not found in the crust of the earth. In the crucibles of particle accelerators and nuclear reactors, elements heavier than uranium were coaxed into being: neptunium, plutonium, americium, curium, berkelium, californium. These synthetic elements, fleeting and unstable, exist for mere moments before decaying into lighter atoms, yet each was mapped and measured, named and numbered, and given a place on the table. The search for new elements carries us to the edge of the possible. As we move to higher and higher atomic numbers, the nuclei of atoms groan beneath the weight of their own protons and neutrons. The forces that hold the nucleus together, strong and delicate, begin to fail, and the atom becomes unstable, prone to fission, decay, transformation. Here, at the table's ragged fringe, the islands of stability are few and far between. Chemists and physicists dream of the island of stability, a theorized region where super-heavy elements might last long enough to reveal new properties, new forms of matter, new chemistry. But for now, these elements are ghosts, glimpsed for a heartbeat in the detectors of distant laboratories, their names a litany of human ambition: nihonium, moscovium, tennessine, oganesson. Yet the table is not merely a list of what is, it is also a challenge, a question posed to future generations. What else lies beyond? Why do the elements arrange themselves so? Are there limits yet undiscovered, patterns yet unrecognized? Even now, debates flicker among scientists. Should the table be redrawn to better reflect quantum reality? Should hydrogen float over the carbon group, or perhaps stand alone, a category unto itself? Might there be elements with properties so strange that they demand an entirely new framework of understanding? The table's organization itself is a palimpsest, written and rewritten as knowledge grows. Mendeleev, in his original vision, arranged the elements by atomic weight, leaving gaps for the undiscovered, predicting their properties with uncanny accuracy. Later, the table was reordered by atomic number, the count of protons in the nucleus, revealing a deeper periodicity. Today, some propose three-dimensional tables, spiral tables, or even fractal representations, each seeking to capture the underlying logic with greater fidelity. But every scheme is a compromise, a model that reflects some truths while obscuring others. The periodicity that seems so perfect is blurred by quantum quirks and relativistic effects, especially among the heaviest elements. The simple rules that govern the filling of electron shells begin to break down. Gold gleams with an unearthly luster. Mercury is liquid at room temperature, both effects of electrons moving near the speed of light, their masses distorted by Einstein's equations. Thus, the table is at once a triumph and a mystery. It is a distillation of knowledge, an inventory of the known, but also a frontier, a boundary where the familiar shades into the unknown. Each element is a story, a possibility, a promise of discovery. The table holds not just the substances that make up our world, but the principles that govern their behavior, the symmetries and asymmetries that shape the fabric of reality. In this vast symphony, the limits of our understanding are as important as its harmonies. Science is not static. It is an unfolding process, a conversation between what is known and what is suspected, between the regularities that reassure us and the exceptions that unsettle us. Every blank space, every anomaly, every fleeting super-heavy atom is an invitation to wonder, to probe, to dream. As you drift along the rows and columns, let your imagination linger on those elements that have not yet been seen, on the patterns that have yet to be understood. The periodic table, serene on the wall of a classroom or flickering on a screen, is a living document, a testament to human curiosity and the restless urge to find order in the cosmos. Its symphony is unfinished, its melody unresolved, awaiting the next note, the next discovery, the next leap into the unknown. So let the table whisper to you as you rest, its patterns and mysteries swirling in the quiet spaces of thought. What new harmonies might be found? What deeper logic lies behind the elements' arrangement? The next movement of this symphony beckons, a journey not just through matter, but through the forces that bind the universe together, through the secrets that matter is still waiting to reveal. The ancient dreamers who first wondered at the fire, the water, the solid earth, and the invisible air could not have imagined the elaborate latticework of understanding that would one day blossom from their primal questions. Each element, once thought to be an irreducible essence, now revealed as a unique arrangement of subatomic particles, a chapter in the grand story of matter. But such revelations were not handed down all at once, nor did they arrive as the outcome of a single inspired mind. The periodic table, that elegant map of elemental properties, grew from centuries of probing, failure, and discovery. Tonight, let us drift through the candlelit laboratories and thunderous lecture halls of history, where experimenters and theorists, armed with their evolving tools, pressed ever closer to the heart of elemental mystery. In the flickering half-light of an 18th century study, glassware glints atop a wooden bench. Here, Joseph Priestley holds his bell jar over a shallow pool of mercury, curious about the airs that seem to arise and vanish under different conditions. The tools at his disposal are rudimentary by our standards: simple bell jars, a pneumatic trough, pieces of wood and rubber, and the keen edge of his own observation. Yet with these he isolates a strange new gas, one that allows a flame to burn brighter, a mouse to live longer. Priestley calls it dephlogisticated air, but the world will come to know it as oxygen. Around the same time, across the Channel, Antoine Lavoisier's scales are settling, measuring with care the weights of substances before and after combustion, The French chemist's relentless insistence on mass conservation, his precise balancing of chemical equations, signals a new era, from philosophy to quantification, from speculation to measurement. The elements, Lavoisier proclaims, are substances that cannot be broken down further by chemical means. Candidates for this club are tested, weighed, and admitted by experiment, not by tradition. The air itself, once imagined a simple singular ether, is revealed as a mixture. Nitrogen, oxygen, argon, carbon dioxide, each separated, captured, and catalogued through clever manipulation of temperature, pressure, and chemical affinity. The tools multiply: retorts, crucibles, water-filled troughs, and most importantly, the balance. The era of weighing and precise measurement is underway, and with it, the possibility of comparing the basic building blocks of matter with a new mathematical rigor. Through the 19th century, chemistry becomes a discipline of both the laboratory and the lecture hall. Glass blowers shape ever more intricate flasks and tubes. The Bunsen burner, invented by Robert Bunsen and Peter de Saga, allows for controlled, smokeless heat. The flame's color and intensity become diagnostic tools, the forerunners of today's spectroscopic techniques. The chemist's hands now wield pipettes, burettes, and analytical balances that can measure a feather's weight in silver. In these hands, the elements are coaxed from ore and solution, their properties teased out by systematic investigation. It is in the crucible of these experiments that patterns begin to emerge. John Dalton, a quiet Quaker schoolteacher, brings together decades of observations and proposes his atomic theory. Each element, he suggests, is made of its own unique type of atom, tiny, indivisible spheres, different only in weight. Dalton's atomic weights are rough, but they offer a new quantitative language for chemistry. No longer need the practitioner rely solely on the senses. Reactions can be written as equations, atoms as numbers, matter as ratios. But it is not enough to know that elements exist. The chemists of the 19th century yearn for order, for a natural taxonomy. They observe that certain elements seem to share properties. Lithium, sodium, and potassium, for example, are all soft, reactive metals that fizz and dance upon water. Chlorine, bromine, and iodine are pungent colored gases or solids, all toxic, all ready to combine with metals to form salts. What hidden symmetry governs these families? The answer is revealed not in a single flash, but in a sequence of insights, each building upon the last. Johann Dobereiner, in the 1820s, notices triads, groups of three elements whose properties seem to fall into a progression. The atomic weight of strontium, for instance, is nearly the average of calcium and barium. Jean-Baptiste Dumas and others expand the idea, searching for larger groupings, but the pattern remains elusive. A century's worth of experiments accumulate, each adding a puzzle piece. The laboratory is now a place of both danger and delight. Sodium explodes in water, chlorine gas poisons the unwary, yet the prize is knowledge itself. Chemists such as Robert Bunsen and Gustav Kirchhoff invent spectroscopy, splitting the light emitted by heated elements into vibrant bands of color. Each element, it turns out, has a unique spectral fingerprint, a barcode of light. Suddenly, the periodic table is not just a catalogue of things touched and weighed, but also of things seen and measured at a distance. The element cesium is discovered not by its chemistry, but by its brilliant blue spectral lines, as is rubidium by its deep red. With the tools of measurement and detection growing ever more sensitive, the catalogue of the elements lengthens. Still, the urge for system persists. In the 1860s, a Russian chemist named Dmitry Mendeleev, working in the chill of St. Petersburg, lays out cards on his desk. Each lists an element, its atomic weight and its known properties. Mendeleev shuffles and reshuffles, searching for a pattern, and at last he sees it. When arranged by increasing atomic weight, the elements fall into recurring groups. Their properties, like a melody repeating in a different key, echo down the rows. Mendeleev's periodic table is born, not merely a record of known substances, but a predictive map with gaps that hint at elements still unseen. Mendeleev's genius lies not just in his arrangement, but in his willingness to trust the pattern over the data. Where the sequence calls for an undiscovered element, he leaves a blank. He predicts the existence and properties of eka-silicon and eka-aluminum, and within years, germanium and gallium are found, matching his forecasts with uncanny precision. The table becomes more than a summary. It is a tool for discovery. Other forms of the periodic table are proposed, each reflecting the reasoning and prejudices of its creator. Julius Lothar Meyer arranges elements by their valence, the combining power evident in their compounds. John Newlands notices a law of octaves, an echo of musical harmony, though his idea is at first dismissed as fanciful. Yet, in the end, it is Mendeleev's scheme that endures, expanded and refined as new elements are discovered. The tools of the chemist continue to evolve. By the dawn of the 20th century, the cathode ray tube flickers in darkened rooms, ushering in the age of atomic physics. J.J. Thomson's experiments show that atoms contain smaller components, electrons, tiny carriers of negative charge. Ernest Rutherford, with his gold foil experiment, reveals the atom's nucleus, dense and minuscule, surrounded by a cloud of electrons. The periodic table, once thought to be anchored by atomic weights, is shown to be more fundamentally organized by atomic number, the count of protons in the nucleus. Henry Moseley, using X-ray spectroscopy, proves this with elegant clarity. The frequency of X-rays emitted by each element increases in a simple progression with atomic number, not atomic weight. With this revelation, the last anomalies vanish. Elements that had seemed out of place, such as tellurium and iodine, whose atomic weights defied the pattern, are now seen to fit perfectly when arranged by atomic number. The periodic law is redefined. The properties of the elements are a periodic function of their atomic numbers. Meanwhile, the tools grow ever more precise, ever more capable. The Geiger counter crackles to life, revealing the presence of radioactive elements. Marie and Pierre Curie, working tirelessly with ton after ton of pitchblende, isolate radium and polonium, opening the door to the actinides and the study of radioactivity. The periodic table stretches, its edges curling outward to admit the transuranic elements, synthesized in cyclotrons and nuclear reactors, atoms forged not in nature but by the hands of humankind. Spectroscopy, once limited to the colors of a flame, now encompasses the entire electromagnetic spectrum. Ultraviolet, infrared, X-ray, and later neutron activation analysis all become tools for probing the identities and behaviors of the elements. Mass spectrometers, with their whirring magnets and vacuum tubes, allow for the measurement of atomic masses to a precision undreamed of by Dalton or Mendeleev. The subtle differences between isotopes, atoms of the same element with different numbers of neutrons, are teased out and catalogued. The table itself transforms. What was once a static chart on the schoolroom wall becomes a dynamic, multidimensional landscape. The noble gases, once thought to be inert and unreactive, are coaxed into forming compounds under the right conditions. The rare earths, lanthanides and actinides, are wrenched from their ores and arrayed in their own subseries, their chemistry understood only after decades of painstaking separation and analysis. The tools of the modern chemist are as varied as the elements themselves. Scanning tunneling microscopes allow us to see and manipulate individual atoms, arranging them like beads on a string. Particle accelerators smash nuclei together, birthing elements never before seen on Earth and lasting only fractions of a second. Computers hum and whir, simulating the quantum dance of electrons and predicting the properties of yet undiscovered elements. but the spirit of experiment remains, the willingness to ask, to test, to doubt, and to measure. Each new device, each refined technique is a lens through which the periodic table comes into sharper focus. The ancient alchemists' dream of transmutation, of turning base lead into shining gold, is realized in the modern laboratory not by mystical means, but by the careful rearrangement of protons and neutrons. Still, the periodic table is not merely a record of what has been found, but an atlas of what might yet be. Its empty spaces and unfilled rows beckon the curious, the ambitious, the restless. The tools with which we probe its mysteries are as much a testament to human ingenuity as the table itself. From Priestley's bell jar to the particle collider, from Lavoisier's balance to the scanning tunneling microscope, each has played a role in peeling back the layers of matter, revealing the structure beneath. And so, as the laboratory lights dim and the hum of equipment fades, the periodic table stands both as a monument to what has been achieved and as a signpost pointing forward. What new elements await discovery at its ragged edge? What novel tools and clever experiments will the next generation devise to press further into the unknown? The elemental mysteries endure, inviting us onward, deeper into the subtle architecture of matter and the uncharted realms beyond the visible chart. Here, on the threshold, with every tool in hand and every sense attuned, the story continues, one experiment, one revelation at a time. In the quiet hush of night, when the world softens and the mind turns inward, let us ponder the elements, not as mere symbols in rows and columns, but as ancient whispers, as the deep-boned memory of the universe itself. For the periodic table, so often reduced to a chart on a classroom wall, is in truth a cosmic ledger, a grand ledger of existence, each square a chapter in the story of matter, each element a verse in a poem that began long before the first human gaze searched the stars. If you close your eyes, you might sense the invisible threads that bind us to the elements. They are not abstractions, not distant curiosities, but the very substance of our bodies and our breath. Trace a hand across your chest and feel the gentle rise and fall of your breathing, oxygen made in the hearts of ancient stars, now coursing through your blood, feeding the quietly burning fires in each cell. Carbon, the black graphite in a pencil, the diamond in a ring, and the scaffold of every living molecule, this too was forged in the crucible of cosmic explosions, only to become the backbone of DNA, the architecture of life. Hydrogen, the simplest and most ancient, is the element of beginnings. The universe, in its infancy, was little more than a swirling, expanding sea of hydrogen and a dash of helium. Every atom of hydrogen in your body is older than the Earth, older than the Sun. Each began as a particle in the first seconds after the Big Bang, a lone wanderer through eons of cosmic evolution. When you drink water, you are sipping the ancient hydrogen, paired with oxygen, each molecule a tiny relic of the universe's dawn. The periodic table, in its silent symmetry, tells us a story not just about matter, but about transformation. Consider the alchemy of stars. In their blazing cores, nuclear fusion presses hydrogen atoms together, overcoming the fierce repulsion of their like charges, until they merge to create helium. In this act, a fraction of their mass is lost, released as radiant energy, the light that warms planets and kindles life. As the star ages, it crafts heavier and heavier elements, carbon, oxygen, neon, magnesium, layer upon layer, like pages in a cosmic diary. When at last the star's life ends in a supernova, an explosion so powerful it momentarily outshines a galaxy, still heavier elements are born. Iron, copper, gold, uranium. These are flung out into the galaxy, dust and debris that will become the seeds of new stars, new worlds, new possibilities. We are made of that debris, the iron in your blood, the calcium in your bones, the potassium firing in your nerves. These atoms come not from the earth, but from the hearts of long-dead stars. To say that we are star stuff is not a poetic flight, but a literal, scientific truth. The periodic table is our family tree, its branches reaching across billions of years, its roots sunk deep in the furnace of creation. Yet it is not only the origins of elements that link us to the cosmos, but their patterns and properties, order arising from seeming chaos. The arrangement of the periodic table was Mendeleev's triumph, but the underlying order he sensed was written by the universe itself. It is in the shells of electrons, the quantum rules that dictate how atoms combine, how they shimmer and bond, how they build the infinite variety of matter. The table's elegant logic is a map of possibility, why sodium and chlorine, so different alone, become table salt, why carbon forms graphite and diamond, each with such distinct form and function, why a trace of iodine is vital for life, while a whiff of fluorine is deadly. Notice, too, the curious dance of abundance. The universe is not a random jumble of elements. Hydrogen and helium are the most plentiful, the simple children of the Big Bang. Oxygen is common, marrying with hydrogen to form water, the solvent of life. Carbon, versatile and unyielding, is the element of complexity, its tetrahedral geometry allowing it to link in chains and rings, to build proteins and sugars, the foundation of every living thing we know. Rarer elements, like phosphorus, necessary for DNA, or molybdenum, a catalyst in the machinery of cells, are precious, scattered like jewels, each playing an indispensable role in the delicate choreography of life. There is a profound symmetry here, a resonance between the periodic table and the living world. Consider the elements that make up the bulk of your body: oxygen, carbon, hydrogen, nitrogen, calcium, phosphorus. This handful of elements, out of more than 100, forms nearly everything you see in yourself and in the creatures around you. The same elements that shape the blades of grass, the wings of a dragonfly, the wood of a tree, are the ones that build your heart and mind. The periodic table is not only a catalogue of substances, but a palette with which life paints its infinite forms. But the table is not static, not a finished symphony. It is a living document, a record of discovery and mystery. The blank spaces that once haunted Mendeleev's version have over the decades been filled in, some by chance, some by design. Elements like technetium and promethium, absent from nature and conjured only in the heart of stars or in the crucibles of laboratories, speak to the ingenuity of human curiosity. The heaviest elements, perched at the edge of the table, exist only for moments, their atoms blinking into existence and then decaying in a silent, invisible dance. They hint at islands of stability yet to be reached, at new chapters waiting to be written. To contemplate the periodic table is to contemplate connection. It is to see that the world is not made of separate things, but of relationships between atoms, between elements, between stars and planets and people. Chemistry is the science of bonding, of coming together and breaking apart, of transformation and renewal. Each reaction, each formation of a molecule is a small echo of the grand transformations that shaped the cosmos, a microcosm of creation and change. This sense of connection extends beyond the physical, for as we probe the elements, as we learn to harness their energies, to shape them to our needs, we become a part of their story. The silicon in your phone or computer was once locked in sand, shaped by volcanic fire, then refined and etched by human hands. The lithium in a battery, the cobalt in a magnet, the gold in a wedding ring. Each carries a legacy of geology and stardust, of human invention and desire. Yet even as we wield the elements, we are shaped by them in turn. The iron in our blood lets us breathe, the sodium in our nerves lets us think, the carbon in our cells lets us grow and dream. We are not separate from the world of matter, but expressions of it, patterns of atoms given consciousness for a fleeting moment. The periodic table, then, is not only a guide to the outer world, but a mirror in which we glimpse ourselves, woven from the same cloth as nebulae and oceans and the dust of moons. Let your thoughts linger on the rare and strange as well. Consider the noble gases, those aloof, unreactive elements that drift at the edge of chemistry's dance. Helium, a silent partner in the fusion that powers stars, is so light that it slips away from Earth itself, escaping to space. Neon, argon, krypton, silent, invisible, yet essential in their own subtle ways, from lighting city streets to preserving the delicate apparatus of science. Their presence reminds us of the richness of the table, of the ways in which even the quietest elements have their place in the harmony of matter. And then there are elements that challenge us, that remind us of the limits of our knowledge. Radioactive uranium and thorium, whose slow decay warms the Earth's core, drive the shifting of continents and the eruption of volcanoes. Plutonium and americium, artifacts of human ambition and fear, are both promise and peril, their energies vast and difficult to control. These elements teach us humility, for the power locked within the atom exceeds our grasp, a reminder that mastery over nature is always partial, always provisional. In the dance of elements, life itself emerges as a rare and exquisite possibility. The carbon-based molecules that make up living things are not inevitable, but the result of a precise and delicate alchemy. The periodic table is filled with potential, but only a narrow slice of its offerings is suitable for the chemistry of life as we know it. The possibility of life elsewhere in the cosmos depends on the same principles, the availability of water, of carbon, of the right balance of elements in the right conditions. When we search the skies for signs of life, we are searching for echoes of the same periodic order that builds our own bodies. Yet the elements also whisper of strangeness, of possibilities beyond our own. Could life arise from silicon, as some have speculated, or from chemistries we have yet to imagine? Could there be worlds where ammonia, not water, is the solvent of life, where phosphorus is replaced by arsenic, where life draws its energy from sulfur rather than sunlight? The periodic table, with all its order, leaves room for mystery, for the unknown, for the not yet discovered. In its structure is both a map of what is and an invitation to wonder at what might be. So as you lie in the darkness, let your mind drift through the lattice of the periodic table. See the hydrogen, born at the universe's birth, still burning in the stars overhead. Feel the oxygen, breathed by trees and by you, cycling through air and water and life. Imagine the carbon, linking and relinking, building bones and leaves and brains. Contemplate the gold and uranium, the neon and iodine, each carrying a tale of cosmic violence and quiet transformation. In each element, a fragment of the universe's history, a piece of your own story. The periodic table is not only a tool for chemists, not only a list for memorization. It is a testament to the unity of matter, to the kinship of all things, to the continuity that binds atoms to cells, stars to people, the infinite to the intimate. It is a reminder that in knowing the elements, we are learning the language of the cosmos itself, a language written not in words, but in the silent, ceaseless dance of particles and forces. As the night deepens and sleep draws near, let the quiet order of the elements settle in your thoughts. Remember that you are not separate from the world, but a part of it, woven from the same atoms, shaped by the same forces, a brief and beautiful expression of the universe's endless creativity. The periodic table, in its silent rows and columns, is a map not only of matter, but of meaning. Its story continues, as does yours, in the ever-unfolding mystery of existence, where every atom is a question and every breath a connection. As our journey through the A to Z of the periodic table gently drifts to a close, each element's story glimmers like a comet tail fading into the hush of space. May these cosmic whispers of matter and magic lull your mind into peaceful wonder, and when you return, more Dreamtime tales will await to carry you softly through the mysteries of the universe.